Okay, we're going to talk about something called Pascal's triangle, which maybe some of you remember this from last year if you were in Algebra 2 last year. We talked about Pascal's triangle last year and kind of how to use it when we were working with polynomials and how to like quickly multiply polynomials instead of having to do like distributing a bunch of times or like the box method if maybe you saw that last year. So in your notes here, this kind of just shows you what Pascal's triangle looks like, and we're going to fill it out. But basically, Pascal's triangle is a pattern of numbers. And like it says up here, it was discovered in the 13th century, so a long time ago. And each number in the triangle is the sum of the two numbers diagonally above it. All the outside numbers on Pascal's triangle are always ones. So the triangle always starts with a 1 and ends with a 1 on the left and the right side. We also have the Pascal's triangle broken into rows. So we have like row 0, row 1, row 2, and so on. And those come into play when we start looking at what we're trying to expand and its exponent. So row 0 would be if something had 0 as an exponent, because anything raised to the 0 power is always a 1. So that's why the top of your triangle starts with a 1. But then the next row, it kind of also has 1s on either side. And then underneath that is where you can really start to see the pattern. So like this 2 in the middle, that was created by adding those two 1s diagonally from it. And then that keeps going down below here. So like the 3 was created by adding the 1 and the 2, and same here, 2 and the 1. So they want us to fill in the next row. And so using that pattern, we know that the first and last are going to be 1s, and that's going to be for both row 4 and row 5. And then to find those middle numbers, we have to start adding the numbers that are diagonal above it. So like for this box here, we would add the 3 and the 1, and we'd get 4. What is the middle box going to say? 6, and then this one should be 4. Okay, how about the boxes down here for row 5? 5. Good, 10, 10, 5. Good. And it keeps going. Okay, it doesn't stop at row 5. I mean, there's an unlimited number of rows to Pascal's triangle. It just gets bigger and bigger and bigger. And like last year, I know for my class, I showed them a really big picture of Pascal's triangle. So you can find it, especially if you need to use maybe the bigger rows, and we might have to do that a little bit later. You can either try to create the rows, especially if they're really large and it's not shown on there, or like when you're working on homework of that, you could probably just Google Pascal's triangle and like see a quick picture if you want to see what the rows are. But just know, like if you don't have access to that, you can always create the rows yourself because there's a distinct pattern to it. So when you're expanding a binomial, which would be something that has two terms, okay, and it's raised to a power. So like the example they have here is this a plus b raised to the third power. We could go about this the really long way if we wanted to. We could write out a plus b 3 times. And then what I would really have to start doing is distributing and like multiplying together. But the reason why Pascal's triangle was created is to shortcut that. So we don't have to go through the tedious process of multiplying a whole bunch of times. Because even if you think through how you would do this, you would have to pair up the first two maybe together, and you'd have to multiply those first. And you guys could FOIL it. Like you could do your first, your outside, your inside, your last terms. You could do that whole thing. And then whatever you get here, you're going to have to multiply that to the next one. So I'm just going to shortcut this. If I were to FOIL these first two, it comes out to be a squared plus 2ab plus b squared. Okay, and that's after like you multiply all the terms and you simplify it. Then I would have to take this and I would have to multiply by that third a plus b. And then I would have to either distribute or I'd have to maybe set up like the box method to multiply these. And eventually when you get that, like after you multiply everything, it comes out to be a to the third plus 3a squared b, 3ab squared, and then plus 3b, plus b to the third. No 3. Again, I shortcutted my way through that because I've already gone through the process of multiplying before. Now you can imagine if I had a plus b raised to the 7th power, this is only going to start to get really massive, right? Because you're going to have to multiply even more times. And it starts to just become like a really big, huge headache because you have all these things that you're trying to multiply. So if we look at the coefficients, which remind me, what's a coefficient? Where do you find coefficients at? In front of the variables, the numbers that are sitting in front of the variables. So we have a 1 in front of the a to the third. So we have a 1 there. We have a 3, and then another 3, and then we have another 1. If we look back up at our triangle, that matches row 3 that we saw up there. 1, 3, 3, 1. So because we're recognizing that pattern, we can use Pascal's triangle to help us kind of shortcut this. Okay? Now, technically, how this works, guys, especially since we've been talking a lot about probability and statistics and that in this unit, remember when we talked about permutations and combinations at the very beginning? Pascal's triangle is technically a whole bunch of combinations happening over and over and over again. Okay, so this kind of shows you what that looks like if I was just looking at the formula and doing this with the long-handed way. So if I had something like a plus b raised to the n power. So a and b could be numbers, they could be letters, they could be a combination of letters and numbers, and then n is an exponent, and it could be any number that I wanted it to be. What this is showing you here is that it's really breaking apart each term and writing it in a combination form. So when we did that combination formula before, you were kind of using that in this sense to make this Pascal's triangle. So I just want to talk through where they're getting all these pieces from. So if you just look at this first term that I'm boxing up here, that C represents combination, okay? The N, that's coming from the exponent that's on the outside of your binomial. So that's like your total that you're choosing from. And then you always start at 0. So that's why they have a 0 here. And then you'll even notice like going forward that they go up by 1 at a time. So like up to 1 to 2. And then it goes up to whatever your exponent is. So if this was something raised to the 5th power, I would go up to 5C5, like 5 choose 5. Okay, so that n at the very end just represents how many times you would have to do this to finally get to the end. Then you'll notice like n is going to show up in these a and the b, and now the a and the b come from the binomial piece. And again, like I said, that could be a number or it could be a letter. So the a could be like a x and the b could be a 5. So it could be x plus 5 to the 5th power or whatever. And so these pieces are also coming directly from that binomial that we see up above. And then you'll notice, like with the exponents, that they also have a pattern to them. Okay? So again, this is kind of showing you guys, this is the really longhand way that they, did this way long time ago, before they had things like calculators and stuff to help them along. Okay? However, last year, when you learned about Pascal's triangle, you maybe weren't expected to use combinations. Okay? We taught you guys a different method in Algebra 2 in order for you to be able to do this a little bit shorter. So I'm not going to make you guys use the combination form. I just wanted to show you guys what that looks like and where it comes from and how it ties into this unit. What I'm going to show you is what we did last year in Algebra 2 with Pascal's triangle. How can I use just Pascal's triangle and the terms that I see and basically use this pattern without having to do a whole bunch of combinations? So for example, it says a plus b, and it's raised to the 5th power for this first one. So what I do first is I look at that exponent. The exponent is a 5. That means I'm going to need row 5, which we wrote out up above. What were the numbers that we wrote out for row 5?
1, 5, 10, 10, 5.
Okay, so here's what I like to do. I like to write those out and give yourself a little bit of space. Don't cram them together. So I'm going to write 1, 5, 10, 10, 5, and 1. Then what I do is I take the terms that are inside of those parentheses. So I take that binomial term and I split them apart. And here's how I handle it. I start with the first term in my parentheses, which in this case is the a. And I put that underneath the 1. And that is going to get your 5 from your binomial up above. That's the exponent. And then as you work your way down, that 5 should decrease by 1 every single time. So the next one's going to be a to the 4th, b to the 3rd, not b to the 3rd, a to the 3rd, a squared, a, which is technically to the 1st power, guys. And then there would be no letter here because it would be a to the 0, but that's just 1. So I always told my kids last year, just you don't need to write anything. I just did like a little dash to symbolize it becomes a 1, so it doesn't really affect the problem. So we never worried about it. Now I'm going to do the same thing with the second part here. So the b, but instead of starting at the beginning, we start at the end and we work our way to the left. So b to the 5th power, and then going backwards, b to the 4th, b to the 3rd, b squared, b, and then again, I don't need anything on that first one because again, it would be b to the 0, which is a 1. Does this look familiar to you guys? Okay, so now what we're going to do is you're going to start multiplying in the columns vertically. So I like to group them together just so I kind of know what I'm pairing up here. And this is going to help me get my final answer. Now, when you have things raised to powers, this one's maybe not so challenging because they just gave you letters A and B. So you're not actually having to do a ton of math here. But if it was like 5 to the 5th power, I would actually need to compute that. And we'll get into some of those examples as we get going here. So this first one is just going to be 1 times a to the 5th power, which is just going to be a to the 5th power. I'm going to write that underneath here, a to the 5th. What would the next one say? 5a to the 4, and then your b. Okay. Next one would be
10a to the 3rd, a to the 2nd squared.
Yep. And then the next one.
10a squared. B.
Yep. Then we have plus 5ab to the 4th, and then plus b to the 5th power. And you should hopefully see like there's a pattern happening here. Those coefficients that come from Pascal's triangle are being used, and the letters have a distinct pattern, especially with their exponents. You know, the first term has only an a and the last term has only a b. And everything in the middle, there's this pattern between them, between how the numbers are increasing and decreasing respectively for the letters. Okay, but this is your answer. And that is a whole lot shorter than having to multiply them out 5 times. It saves you a lot of work. And instead of doing it also like with a bunch of combinations, which we could, you're going to get the same answer here. Because the combination really, all that's going to do is work with the numbers that are in your problem, especially if they start giving you things more complicated than like a plus b. Okay. All right. I'm going to actually skip over number 2 for right now because I want to go to the back because I want to get to some that actually deal with more than just letters. So I actually want to skip all the way down to number 4 because this is going to start throwing in things that don't just have X's and Y's or A's and B's. They're actually going to have numbers in here, and so we need to be able to work with them. So for the 4, it says x minus 3 to the 6th power. Now, we didn't have the 6th row in our Pascal's triangle in our notes, so you either need to create it or use your resources and look it up, okay? But we don't need to look it up right now. We should be able to figure out what our coefficients are. What do you guys, you're going to start with a 1.
1, 6, 15, 20, 15, 6, 1.
Everyone agree with that?
Yeah.
I got to look at it. 1, 6, 15, 20.
Yeah.
15, 6, 1. I agree.
That's what I had to do.
You have that memorized? You do? You're so smart. Okay, let's figure this out then with our terms. So underneath the 1, we're going to start with the x, and it's going to be x to the 6th power. And then we're going to gradually go down 1 at a time. And that last one, we don't have an x. If you ever get to the last term and you have room for whatever your piece is here, you did something wrong. You need to go back and fix that, okay? Because that last one should never have the first term in it. Okay, and then we're going to have this 3. Now, we got to be careful with this one because you guys see how it's a minus up here and not a plus? So really what we're doing is it's a negative 3. So be careful with the signs. If it was a plus sign, I wouldn't be mentioning this, but because there's a minus sign, technically what you're doing is a negative 3 to the 6th power. So just watch that. And then this would be negative 3 to the 5th power. And we're going to keep going backwards. I always put parentheses around things with negatives because I don't want to miss that sign. And some of you will also see, like when we get to an answer, I'm going to show you a little bit of a shortcut instead of having to work with the negative.
When we like set them up like all together, can we like switch the order, like put like -3 before the x, or does the x have to be like come before?
The x should be, you could put the -3's above the x's if you want, but you still have to put -3's largest exponent on the far right.
Okay.
I mean, you could technically switch them, but if someone read it, it would probably look backwards because like the last term, especially in this one with the -3 to the 6th power, is going to be a number. And most of the time when we have like a polynomial and it's written in descending form, we start with the things with letters first and we end with the number.
Okay.
So if you were to flip it all around, it probably wouldn't, it's not going to affect the terms, but it's going to maybe look backwards when you read it.
Okay.
Does that make sense?
Yeah.
Okay, so now let's start multiplying in our columns here. Okay, so this first one, 1 times x to the 6th power would just be x to the 6th power. Okay, now be careful on this next one because of that -3. You have 6, an x to the 5th power, and a -3. So when you multiply, it's going to become -18. So -18 x to the 5th power. When you have a negative raised to an odd exponent, it's going to keep it negative. If it's raised to an even exponent like we see on the next one, it's going to become positive. Because -3 squared would become a positive 9. What's 9 times 15? 135. Okay, next one, it'd be negative again because we've got an odd exponent. So you got -3 to the 3rd power. So -3 times -3 times -3, and then times 20. How much is that?
-540.
Good, -540, and then that would be x to the 3rd. Okay, now we've got -3 to the 4th power times a 15. The number's going to get bigger. What's it come out to be?
1,215.
Good. And then that's x to the 2nd. And if you need to, especially with these big ones, I would maybe cross off your columns as you're done with it, just so you don't accidentally do the same one twice. Okay, next one, -3 to the 5th power times 6. I have -1,458. You guys agree? Okay, and then x is attached to that. That's that column. And last but not least is that -3 to the 6th power times 1, 729. There's your final answer. Now, something I just want to point out to you. I'm circling these signs in the middle. Do you notice what they're doing? Yeah, they're going back and forth, back and forth, back and forth. So here's what you could do, guys. If you understand what I'm going to say to you, this is another little shortcut that you can take. If you have something, like the second term is minus something, technically you could not worry about the negative inside the parentheses if you know that the signs are going to be flipping back and forth between plus and minus. The only thing that you have to just be careful of is, does it start with a plus or does it start with a minus? And you would have to look at your terms and figure out if that negative was in here, am I raising it to an odd power or to an even power? Because like this one, since you started out with a 6, that first term is raised to the 6th power. The second one is then a 5, and that's odd. So that's why it started out with a minus sign. If this had been like raised to the 9th power instead, 9 starts it off, that's your odd. So the second term would be raised to the 8th power. That's even, so it would technically start with a plus sign and then go to minus, plus. So there's ways that you can maybe like think about that and shortcut it so you don't have to worry about putting in the negative like that. Okay, do we have any questions so far? Okay, I don't want to spend a ton of time on this because like I said, you learned this last year. And so I feel like some of you are like, this looks really familiar. So let's do one more. Let's do number 7 because it's a little bit more complicated and just you've got numbers and letters for both of your terms. So I've got 3p minus 2q to the 5th power. So what's my row 5 coefficients? 1,
5,
10 again,
yeah, for sure.
and then 5, 1. The other thing I just want to point out, this was raised to the 5th power, but how many numbers do we have here? 6. When we came up here, I'm just going to scroll back up for a second. This one was raised to the 6th power. How many numbers did we start out with here? 7. So just another pattern to maybe be aware of. That's always going to happen in Pascal's triangle. The coefficients should be one more than what your exponent is. Okay. So 3p is going to be your first term, and that's going to be to the 5th power. And then we're going to go down one at a time. And I'm putting parentheses around all of this because you got to do it to both terms, not just to the number or not just to the letter. It has to go to both. So I always put that in there because I just want to make sure that we're keeping track of that. Okay, and then we're going to start on the right and go backwards. And I am going to use the negative just in case you didn't follow what I was saying earlier about how to work with the signs. Okay, let's start multiplying here. This first term isn't so bad. Remember though, and if this is something that you need to do, this 5 is going to go to the 3 and to the p. So both of those terms get raised to the 5th power. Not just the number or not just the letter. So 3 to the 5th power is what?
243.
243. And then we'd have p to the 5th. Okay, now on the second term. So I'm done with this. I'm going to cross it off. So on the second one here, just like before, that 4 on the outside, that goes to the 3 and it goes to the p. The negative 2q we'll have to think about that too, but right now this was just raised to the 1st power, so it doesn't really get impacted right now. So 3 to the 4th power is 81. So you're going to have 81 there, times the 5 up on the top, and then times that negative 2. So 81 times 5 times negative 2, I got negative 810. And then it should be p to the 4th q. Okay, so why don't you guys take like 2 minutes here and see if you can finish expanding this.
See if it goes faster.
Okay, so I wrote out mine. Hopefully ours matches. Anyone else get the same thing as I did? Cool. Oh, you're right. It would be negative 32. I missed that down there. That should be a minus. Okay.